Are you interested in astronomy? Then these 10 space facts are for you. Let's go. The cosmic microwave background radiation is nearly uniform in all directions, with tiny temperature variations providing valuable information about the early universe's structure. Right, the near uniformity of the cosmic microwave background, CMB, radiation is indeed fascinating, but the tiny variations hold the key to unlocking the secrets of the early universe. Imagine the universe right after the Big Bang. It was incredibly hot and dense, filled with a hot soup of elementary particles. As the universe expanded and cooled, it eventually reached a point where it became transparent to radiation. This is the CMB radiation we detect today. The remarkable uniformity of the CMB tells us that the universe was very uniform in its early stages. Almost every direction we look in space, the CMB temperature is nearly the same. This uniformity is consistent with the idea of a rapid and immense expansion, which evened things out in the early universe. However, the CMB isn't perfectly uniform. There are very small variations in temperature, about parts per 100,000. These tiny fluctuations are incredibly important. They are like ripples in the fabric of space-time, and they are thought to be the seeds for the formation of all the structures in the universe, from galaxies to clusters of galaxies. By studying the patterns of these fluctuations, scientists can learn about the initial conditions of the universe. The distribution of hot and cold spots tells us about the density variations that existed way back then. These variations eventually grew due to gravity, pulling matter together and forming the large-scale structures we see today. The CMB is essentially a fossil light echo from the early universe. By studying its properties, we can probe back in time to a period just a few 100,000 years after the Big Bang. It's like having a snapshot of the universe in its infancy. Scientists use sophisticated instruments and telescopes to measure the CMB with incredible precision. These measurements are helping us to refine our understanding of the Big Bang model, test theories of inflation, the rapid expansion period, and constrain the properties of things like dark matter and dark energy. The CMB is a powerful tool for cosmological studies, and ongoing missions and data analysis are constantly revealing new insights into the origin and evolution of our universe. Cosmic dust, primarily composed of silicate and carbonaceous grains, contributes to the formation of planets and stars and can be observed through infrared and microwave observations. Cosmic dust plays a crucial role in the grand story of universe's creation and continues to be an active participant. Cosmic dust is a complex mixture of tiny particles, ranging from microscopic to millimeter-sized. The two main types of grains found in dust are silicate grains. These are the most abundant type, composed of minerals similar to rocks found on Earth, like olivine and pyroxene. They are formed in the hot environments around dying stars or during stellar explosions. Carbonaceous grains. These are rich in carbon and contain organic molecules, the building blocks of life. They are thought to form in cool, interstellar clouds or around stars rich in carbon. In addition to these main types, cosmic dust can also contain ice particles, metallic grains, and even presolar grains, tiny remnants from before the formation of our solar system. Cosmic dust plays a critical role in the birth of stars and planets. Here's how. Cooling the gas, dust grains act as tiny radiators, absorbing light and re-emitting it as infrared radiation. This helps to cool down the hot gas in interstellar clouds, making it denser and more prone to collapse under gravity. This collapse eventually triggers star formation. Building blocks of planets, dust grains clump together in these collapsing clouds, forming the core of a new solar system. Over time, these clumps attract more gas and dust, eventually growing into planets and moons. Cosmic dust is itself invisible, but it interacts with light in ways that allow us to study it. Here are two key methods. Infrared observations. Dust grains absorb visible light and re-emit it as longer wavelength infrared radiation. By studying this infrared glow, astronomers can map the distribution of dust in galaxies and nebulae. Microwave observations. When light interacts with dust grains, it can be scattered or absorbed and re-emitted as microwaves. These observations help us understand the properties of dust in the early universe and trace the evolution of galaxies over time. By studying cosmic dust, we gain valuable insights into the birth of stars and planets, the composition of the interstellar medium, and even the history of our own solar system. It's a fascinating realm of tiny particles playing a giant role in the cosmic story. Before we moved on to the next fact, don't forget to subscribe so you receive even more amazing science facts. The zodiacal light, a faint glow seen in the night sky, is caused by sunlight scattered off dust particles in the plane of the solar system. The zodiacal light is a subtle but beautiful phenomenon caused by dust in our cosmic neighborhood. The zodiacal light is a subtle phenomenon, often overpowered by moonlight or light pollution. However, under ideal conditions, it can be a breathtaking sight. The zodiacal light is best seen during twilight, either shortly after sunset in the west or before sunrise in the east. Look for the faint, cone-shaped glow extending upwards from the horizon along the ecliptic. The light is more visible from darker locations with minimal light pollution. If you live in a city, head out to a rural area with clear skies for the best chance of spotting it. In the northern hemisphere, the zodiacal light is most prominent during spring evenings, February-March, and autumn mornings, September-October. During these times, the ecliptic stands at a steeper angle to the horizon, making the zodiacal light more visible. By understanding the zodiacal light, we gain insights into the distribution of dust within our solar system. It's a reminder of the vast amount of material left over from our solar system's formation, and it continues to play a role in the ongoing story of our cosmic neighborhood. Interferometry involves combining data from multiple telescopes to achieve improved angular resolution, allowing astronomers to observe fine details in distant objects. Interferometry is a powerful technique that pushes the boundaries of astronomical observation. Imagine trying to see a distant object with just one eye. You wouldn't be able to discern fine details. Now, imagine using both eyes. You gain a much clearer and more detailed picture. This is the basic idea behind interferometry in astronomy. Instead of relying on a single telescope, astronomers combine data from multiple telescopes spread apart to create a virtual telescope with a much larger effective diameter. This larger diameter translates to achieving significantly higher angular resolution, allowing us to see incredibly fine details in faraway objects. The key concept here is angular resolution, which is essentially the ability to distinguish between two closely spaced objects. In telescopes, it's limited by the diameter of the primary mirror or dish. Here's how interferometry breaks this limitation. Baseline matters. The farther apart the telescopes are in an interferometer array, the higher the achievable angular resolution. Imagine the distance between the telescopes as the baseline. A larger baseline creates a sharper image. Interference dance. The light waves collected by each telescope are combined mathematically. This process uses the concept of wave interference, where light waves can reinforce or cancel each other out. By analyzing the interference patterns, astronomers can reconstruct a high-resolution image of the observed object. Interferometry can be applied across different parts of the electromagnetic spectrum, from radio waves to visible light. Here are two main types. Radio interferometry. This is the most widely used type, where radio telescopes spread over vast distances, sometimes continents, or even across the Earth, work together. This technique allows astronomers to study the structure and evolution of galaxies, star formation regions, and even black holes. Optical interferometry. This technique uses telescopes operating at visible or infrared wavelengths. However, due to the shorter wavelengths, the telescopes need to be much closer together, often mounted on a single structure. Optical interferometry is used to study the surfaces of stars, resolve close binary star systems, and directly image exoplanets. As interferometry techniques continue to develop, astronomers expect to push the boundaries of resolution even further, opening up new avenues for exploring the universe and its wonders. The Gaia mission, launched by the European Space Agency, aims to create a 3D map of the Milky Way and provide precise measurements of billions of stars' positions and motions. The Gaia mission, launched by the European Space Agency, ESA, in 2013, is a truly groundbreaking astronomical observatory mission. Its primary goal is incredibly ambitious: to create the most detailed 3D map of our Milky Way galaxy ever made. Imagine having a detailed map of your entire city, showing the location and height of every building. That's essentially what Gaia is doing for our Milky Way, but on a much grander scale. By precisely measuring the positions and motions of billions of stars, Gaia is creating a 3D map that will revolutionize our understanding of the galaxy's structure and evolution. Gaia isn't just mapping locations, it's also gathering a wealth of information about the stars it observes. Here's what kind of data Gaia collects. Positions. With incredible accuracy, Gaia measures the precise positions of stars on the sky. This allows astronomers to track their movements and reconstruct their past and future trajectories. Motions. By observing how stellar positions change over time, Gaia measures the velocities of stars through space. This information helps us understand the dynamics of the Milky Way and the motions of different stellar populations. Brightnesses. Gaia measures the brightness of stars across different wavelengths of light. This allows astronomers to estimate a star's temperature, luminosity, and even its chemical composition. The sheer volume of data collected by Gaia is staggering. It's designed to survey and measure the properties of billions of stars across the Milky Way. This data will be used to address numerous fundamental questions in astronomy, such as galactic structure. By mapping the distribution of stars in 3D, Gaia will help us understand the spiral arms, central bulge, and halo of our galaxy. Stellar evolution. By tracking the motions and properties of stars of different ages, Gaia will provide insights into how stars are born, live, and die. Dark matter. The motions of stars can be influenced by invisible dark matter. By studying the motions of large numbers of stars, Gaia can help us constrain the distribution and properties of dark matter in the Milky Way. The data collected by Gaia is a goldmine for astronomers, not only for the initial goals of the mission, but also for future discoveries. As new analysis techniques and technologies emerge, scientists will continue to mine this data to uncover new insights about our galaxy and its inhabitants. The Gaia mission is a testament to international collaboration in space exploration. Its ongoing observations and data releases are already transforming our understanding of the Milky Way and will continue to shape our galactic view for years to come. The Sun's core is a region where nuclear fusion converts hydrogen into helium, producing the energy that sustains the Sun's radiation. The Sun's core is a powerhouse, the very engine that keeps our solar system bathed in light and warmth. Let's delve deeper into the nuclear fusion process happening there. Imagine a sphere of incredibly hot and dense plasma. That's the Sun's core. The temperature here soars to a scorching 15 million degrees Celsius, hot enough to overcome the natural repulsion between atomic nuclei and enable a process called nuclear fusion. Nuclear fusion is the process where atomic nuclei combine to form a heavier nucleus, releasing tremendous amounts of energy in the process. In the Sun's core, the primary fuel for fusion is hydrogen, the most abundant element in the Sun. The Sun's core is primarily composed of hydrogen atoms, each consisting of a single proton and an electron. Due to their positive charges, protons naturally repel each other. However, the immense gravity and temperature in the Sun's core create an environment where protons can overcome this repulsion and get close enough to fuse. The dominant fusion process in the Sun is called the proton-proton chain reaction. It involves a series of steps where two hydrogen nuclei, protons, fuse to form a heavier isotope of hydrogen called deuterium. This releases a positron, a positively charged electron, and a neutrino, a tiny, almost massless particle. The deuterium nucleus fuses with another proton to form a light isotope of helium, 3. Two helium, 3 nuclei then fuse to form a regular helium, for nucleus, releasing 2 protons in the process. These released protons can then participate in further fusion reactions, creating a self-sustaining chain reaction. The fusion of hydrogen into helium releases a significant amount of energy in the form of gamma rays. These gamma rays travel outward through the Sun's interior, eventually getting converted into other forms of energy like heat and light that radiate from the Sun's surface. Nuclear fusion in the Sun's core is a delicate balance. The immense gravity from the Sun's mass keeps the core under extreme pressure, facilitating fusion. The energy released by fusion counters this gravitational collapse, maintaining a stable equilibrium. The Sun has enough hydrogen fuel in its core to sustain fusion for billions of years. However, as the fusion process continues, the core slowly but steadily depletes its hydrogen reserves. Over time, the Sun's core will eventually exhaust its hydrogen fuel, leading to a series of dramatic changes in its structure and evolution. Understanding the nuclear fusion process in the Sun's core is fundamental to our understanding of stars and their life cycles. It's the very reason we have light and warmth on Earth, and studying it helps us explore the potential of harnessing fusion energy here on Earth for a clean and sustainable future. The first exoplanets confirmed orbiting a Sun-like star were discovered around the pulsar PSR B1257+12 in 1992, demonstrating a diverse range of planetary systems. In 1992, Polish astronomers Alexander Wolszyn and Dale Frail announced the discovery of 2 planets orbiting a pulsar called PSR B1257+12. This was the first definitive detection of exoplanets, and it sent shockwaves through the astronomical community. Pulsars are rapidly spinning neutron stars, very different from our Sun. These newly discovered planets were much heavier than Earth, classified as gas giants. Just a few years later, in 1995, Swiss astronomers Michel Mayor and Didier Queloz made another historic discovery. They detected a planet orbiting 51 Pegasi, a Sun-like star located about 50 light-years away. This exoplanet, named 51 Pegasi b, was significantly hotter and closer to its star than any planet in our solar system. It was the first confirmed exoplanet orbiting a star similar to our Sun, demonstrating the existence of planetary systems beyond our own and the potential for a wider diversity of planetary types. Both the 1992 and 1995 discoveries were crucial in revolutionizing our understanding of planetary systems. Here's why. Confirmation of exoplanets. The 1992 finding definitively proved that planets existed outside our solar system, shattering the notion that our solar system was unique. Diversity of planetary systems. Both discoveries showcased the possibility of a wide range of planetary systems. The 1992 find showed massive planets orbiting pulsars, while the 1995 discovery presented a hot Jupiter orbiting a Sun-like star. These discoveries opened the floodgates for exoplanet research. Since then, astronomers have found thousands of confirmed exoplanets, with many more detections waiting to be confirmed. The search continues, revealing a universe teeming with diverse planetary systems, some potentially harboring conditions suitable for life. Some natural satellites in the solar system, such as Jupiter's moon Europa, are thought to harbor subsurface oceans that could potentially support life. Europa, one of Jupiter's many moons, is a fascinating world that intrigues astrobiologists. Here's why. As subsurface ocean, Europa is believed to have a vast subsurface ocean, possibly containing twice as much water as all of Earth's oceans combined. This subsurface ocean is thought to be salty and liquid due to the tidal heating caused by Jupiter's immense gravity constantly pulling and squeezing Europa. Potential habitability, the presence of liquid water, along with the possibility of hydrothermal vents spewing chemicals into the ocean, makes Europa a prime candidate in the search for extraterrestrial life. Icy shell, a layer of ice, likely ranging from 10 to 15 miles, 15 to 25 kilometers, thick, covers Europa's subsurface ocean. This icy shell is thought to be dotted with cracks and fissures, hinting at the possibility of plumes of water erupting from the ocean below. Scientists are particularly interested in Europa because it combines three key ingredients for life as we know it: liquid water, essential elements like carbon and nitrogen, and a potential energy source in the form of hydrothermal vents. While we don't have any confirmed evidence of life on Europa yet, ongoing missions like the upcoming Europa Clipper by NASA are specifically designed to investigate its potential habitability. The exploration of Europa is still in its early stages, but it is a world with the potential to hold revolutionary answers to one of humanity's most profound questions: are we alone in the universe? A significant portion of the mass in the universe can be attributed to dark matter, a form of matter not directly observed, but inferred from its gravitational effects on visible matter. Dark matter is one of the greatest mysteries in our universe, a vast component that we can't directly see but strongly suspect is there. Imagine a massive, unseen entity shaping the universe's structure through its gravity. That's the concept of dark matter. We can't directly observe it with telescopes or any current technology, but its presence is undeniable due to its gravitational influence on visible matter. Here's how astronomers have pieced together the existence of dark matter. Galaxy rotation curves. Stars at the outskirts of galaxies shouldn't be orbiting as fast as they do based on the visible mass of the galaxy. This discrepancy suggests the presence of a much more massive, invisible component, dark matter, that provides the extra gravity needed for these stars to maintain their orbits. Galaxy cluster collisions. When galaxy clusters collide, the visible matter collides and slows down. However, the galaxies themselves remain mostly intact, suggesting that a collisionless form of matter, like dark matter, is dominant and passes through each other during such events. Gravitational lensing. Massive objects like galaxies bend light due to gravity. By studying how light from distant objects is warped by intervening galaxies, astronomers can map the distribution of matter, including dark matter, within those galaxies. Estimates suggest that dark matter could constitute roughly 85% of the total matter in the universe. Visible matter, like stars, planets, and gas clouds, makes up only a tiny fraction, around 15%. Dark energy, another mysterious component causing the universe's expansion, is estimated to comprise the remaining 5%. Despite overwhelming evidence for its existence, the nature of dark matter remains a complete mystery. Scientists have proposed various candidates for dark matter particles, such as weakly interacting massive particles, WIMPs, or axions. However, no confirmed detection of a dark matter particle has been made so far. Understanding dark matter is crucial to unlocking a complete picture of our universe's composition and evolution. It's a challenging quest, but ongoing research and new discoveries may soon shed light on this invisible giant that shapes the cosmos. The The study of exoplanets, or planets orbiting stars outside our solar system, has revealed a vast diversity of planetary systems, including gas giants, rocky planets, and potentially habitable worlds. The field of exoplanet research has exploded in recent decades, revealing a universe teeming with fascinating planetary systems far beyond our own. For centuries, humanity could only speculate about the existence of planets orbiting other stars. But with advancements in telescope technology and detection methods, the doors to exoplanet discovery swung wide open. Since the confirmation of the first exoplanets in 1992, astronomers have identified thousands of these alien worlds, and the number keeps growing rapidly. Exoplanets come in a staggering variety of sizes and compositions, unlike the familiar 8 planets in our solar system. Here's a breakdown of some key types. Gas giants. These behemoths are much larger and more massive than Jupiter. Some orbit very close to their stars, scorching hot worlds called hot Jupiters. Others reside farther out, in orbits similar to our outer gas giants. Super-Earths. These rocky planets are more massive than Earth, but smaller than Neptune. They are a hot topic in exoplanet research, as some may reside in the habitable zones of their stars, where liquid water could potentially exist on their surfaces. Mini-Neptunes. These are smaller versions of Neptune, with thick atmospheres, but likely lacking a solid surface. They bridge the gap between super-Earths and gas giants. Rocky planets. While harder to detect due to their smaller size, astronomers are increasingly finding rocky planets, some potentially similar to Earth in size and composition. The holy grail of exoplanet research is finding an Earth-like planet within a habitable zone, where conditions might be suitable for life as we know it. Astronomers use various techniques to detect these distant exoplanets. Here are some common methods. Transit method. When an exoplanet passes directly in front of its star from our perspective, it causes a slight dip in the star's brightness. By measuring these transits, astronomers can infer the size and orbital period of the exoplanet. Radial velocity method. The gravitational tug of an exoplanet on its star causes the star to wobble slightly. By measuring these wobbles, astronomers can estimate the mass of the exoplanet. Direct imaging. In some cases, powerful telescopes can directly image exoplanets, especially young and giant ones, separated by a large distance from their star. A key focus of exoplanet research is the hunt for potentially habitable worlds. This involves searching for planets in the habitable zone of their stars, where liquid water could exist on the surface. Additionally, astronomers look for signs of biosignatures, potential chemical signatures in an exoplanet's atmosphere that could hint at biological activity. The field of exoplanet research is still in its early stages, but the pace of discovery is accelerating. As telescope technology continues to improve and new missions are launched, we can expect to find even more exoplanets, with a particular focus on potentially habitable worlds. Studying these alien worlds will not only help us understand planetary formation processes, but also shed light on the possibility of life existing elsewhere in the universe. It's a truly exciting time for exoplanet research, and the future holds the promise of even more groundbreaking discoveries. That's all for today. Thank you for watching. See you next time.